Hello. In this video, I'll be talking about molecular geometry as it pertains to covalently bonded compounds. In particular, I'll be focusing on the VSEPR model of molecular geometry. So VSEPR is an acronym and it stands for valence shell electron pair repulsion. That's a bit of a mouthful to say, which is why the vast majority of the time you'll hear it referred to either by its acronym or as the term VSEPR. So VSEPR is how I learned to say it back in the day, so that's how you'll most often hear me refer to it. So if you hear me use the term VSEPR, this is what I'm referring to. And the VSEPR model is going to use a geometry that's based off of the number of electron domains that are found around a central atom. So hopefully by now you're pretty comfortable with your Lewis structure drawing, and you'll know that your central atom has branches that come off of it that determine the overall structure. And so VSEPR is going to take that central atom and count the number of domains around it, and the number of those domains is what's going to determine the geometry of the molecule itself. So what is an electron domain then? Well, an electron domain is a bond or a lone pair. And when I say bond, what I mean is it's just an area where we have a bond. So it doesn't matter whether it's a single bond, double bond, or triple bond. As long as there's a bond there, you count that as one domain. And same thing with a lone pair. If there's a lone pair there, you count that as one domain. So that's how you're going to count your domains as you go around your central atom. You want to count your bonds, and you want to count your number of lone pairs. And that's going to determine what your molecular geometry is, based on the number of those domains. So there's going to be a difference between bonds and lone pairs in terms of geometry. So for molecules that have no lone pairs on the central atom, just bonds, their molecular geometry is going to be the same as their electron geometry. But for molecules where there are one or more lone pairs on the central atom, their molecular geometry is going to be called something different from their electron geometry. And we'll look at that in just a second. But just keep in mind that there is a difference between molecular geometry and electron geometry. And electron geometry is tied specifically to the number of domains around your central atom. Molecular geometry is just a little bit different. So let's kind of jump right in. I'll start with the geometries with no lone pairs first, and then we'll look at what happens when we start adding lone pairs to our structures. So first up on our list is going to be the linear geometry. And this is when you're going to have a central atom with two bonds coming off of it with no lone pairs. And the name sort of fits it because it's just like a flat line. And the bond angle, in which the bond angle is just the angle between the bonds coming off of the central atom. And our bond angle for our two bonds here is going to be 180 degrees, which makes sense because it's just a flat line. So linear, pretty basic, and we're looking at just this straight line with that 180 degree bond angle between those two bonds. So a great example of a linear structure would be carbon dioxide, CO2. And this is sort of the approach you want to take when you go about predicting your molecular or your electron geometries. So the first thing you always have to do is draw a valid Lewis structure. If your Lewis structure isn't correct, then your geometry also probably isn't going to be correct. So drawing a valid Lewis structure is crucial in this process of molecular geometry. So we've got our valid Lewis structure here for CO2, and now if I want to determine the geometry of it, I just go to my central atom, which is carbon, and I just count the number of domains around this central carbon. So I've got one domain here, so we've got a double bond. And remember, the fact that it's a double bond doesn't matter. It's just a bond in terms of domain. So this would be one domain, and this would be one domain. So we have a total of two domains, no lone pairs on the central atom, which means we have a linear structure with that 180 degree bond angle for CO2. So next up on our list, with three bonds coming off of the central atom, is the trigonal planar geometry. And here we're going to see a 120 degree bond angle between each of these three bonds going around the central atom. So here we have a nice example of a trigonal planar structure with BF3. Remember that boron can have a lower number of electrons in its valence shell than an octet. So boron doesn't need 8 electrons in the octet. It's fine with just 6, which means it's just fine having these 3 bonds going off to the fluorine with nothing else. So here we see that great trigonal planar geometry with the 120 degree bond angles, and BF3, great example of that in general. So next up on our roster here is going to be when we have 4 bonds going around that central atom, and this is when we're going to have a tetrahedral geometry. And tetrahedral is really where we introduce 3-dimensional properties to our geometry. So before, when we looked at linear and trigonal planar, they were still flat in the plane. They didn't really have any 3-dimensional properties going on. But tetrahedral is where we introduce those. And so with tetrahedral, you're going to have certain elements that are pointing out and certain elements that are pointing towards. So we'll talk about that in just a second when we look at the example. But ultimately now we're starting to think of things more 3-dimensionally than we were before with the other two. So here we can see a really good example of this tetrahedral structure with the methane molecule, CH4. So we've got our central carbon with 4 hydrogens coming off of it. And ultimately, what's going to end up happening is one of the hydrogens is going to be pointing behind the screen. So I'll pick on this hydrogen here. We can think of this hydrogen as pointing behind the plane. So sort of jutting out. So if you were holding it in your hand, it would be pointing away from you. Versus this hydrogen, which I'll pick on here, would be pointing out of the plane towards you. So if you were holding it, it would be facing you. Whereas this other hydrogen would be facing away from you. And that's how we want to start thinking about these geometries in 3 dimensions. And there's actually specific notation that you can use to show this, and it's called wedge dash notation, which I'll show now. So this is the wedge dash notation system, where we draw a blocked in wedge like this, so a colored in wedge shape, which is going to indicate something that's coming towards you as the viewer. So it's coming out of the plane towards you, versus where we're going to use these dashed lines to indicate when something is pointing away from us behind the plane. So here we can see I've replaced the 2 bonds with the wedge and the dash. So this wedge is indicating that this hydrogen is pointing towards us, whereas this hydrogen is pointing away from us. And you're always going to see this with the tetrahedral geometry, where we have one of the bonded elements pointing away from us and one of them pointing towards us. These 2 solid lines here indicate that these 2 hydrogens are in the plane, so they're just flat. So one is just going straight up and one is just going to the side, whereas these 2 hydrogens are pointing either away or towards, depending on whether it's a dash or a wedge. So next up on our list is going to be a central atom with 5 bonds going around it, and this is going to be our trigonal bipyramidal geometry. And what's interesting with the trigonal bipyramidal geometry is now we have 2 different bond angles. We have a 90-degree angle that's called our axial angle, where we're looking at going from the bond going up and the bond going to the side. So the angle between these 2 bonds is going to be 90 degrees. Whereas when we're looking at 2 of the horizontal bonds here going around the central atom, so this bond and this bond, that angle is going to be 120 degrees, and it's called the equatorial bond. So think axial means going up or down, whereas equatorial means going around the central atom. So think equatorial, think equator, think the equator goes around the Earth. The equatorial bond is going to go around the central atom, versus the axial is going up and down. And the bond between those 2 is going to be 90 degrees, versus 120 for the equatorial. So a good example of this trigonal bipyramidal geometry is going to be PCl5, where we have our phosphorus in the middle and the 5 chlorines coming off of it. And here you can see we have an axial bond here between these 2 chlorines, because this chlorine is going up, this one's going to the side. That's going to be our 90-degree bond angle. And between these 2 chlorines going around the phosphorus, that's going to be our equatorial 120-degree bond angle. So great example with the Cl5 of that trigonal bipyramidal. So sort of the biggest we can get here is now with the 6 bonds going around the central atom. This is going to be our octahedral geometry. And the good thing about the octahedral is there's only one bond angle. Every bond is going to have a 90-degree angle between it. So the equatorial bonds are all 90 degrees and the axial bonds are 90 degrees. So you only have to worry about that one angle for everything. So here's an example of that octahedral geometry. And I would say octahedral is really reserved in covalent structures for those elements that can do expanded octets, which makes sense because you're really only going to see more than 4 bonds on elements that can undergo expanded octets. And really, in my experience, that's most commonly going to be elements like sulfur and phosphorus. For some reason, sulfur and phosphorus really love making 5 and 6 bonds with halogens, particularly fluorine. So SF6 is a really good example of that, where you have these 6 fluorines bonded to this central sulfur, and you can see this octahedral geometry with those 90-degree angles all the way around. And like I said, this is as big as they come in terms of number of bonds you can put on that central atom. So now let's start thinking about how things are going to change if we start adding lone pairs onto our central atoms. So up until now, we've just looked at bonds. And we know with bonds, the molecular and the electron geometries are identical. But for these structures where we have lone pairs now on the central atoms, things are going to start changing up slightly. So let's look at when we have 2 bonds and 1 lone pair. And that's what this structure is going to look like. And I've just put the E here to represent any central atom. So we've got 2 bonds coming off and a lone pair sitting on top. And ultimately what you want to do is count the number of domains. So we have 1, 2, 3 electron domains because we have 2 bonds and a lone pair. So when you have 3 domains, your electron geometry is going to be trigonoplanar. So the electron geometry is going to match up with what we had when we just had the bonds, but the molecular geometry is going to be different because this lone pair is going to distort the bond angle. So with a normal trigonoplanar, we would have 120 degrees. But in this case, because of that lone pair, electrons repel one another. That's part of the VSEPR name, electron pair repulsion. So this pair of electrons is pushing the bonds downward because they repel one another. And so with a trigonoplanar, we would normally have 120 degrees, but because of that lone pair, it's going to push the bonds downward, giving us a bond angle of less than 120 degrees. And the molecular geometry for this distortion is going to be called bent. So when you have 2 bonds and 1 lone pair, your molecular geometry is called bent, but your electron geometry is trigonoplanar. And a good example of this bent structure is going to be sulfur dioxide, SO2. Because we have the 2 bonds going to the 2 oxygens, and we have this lone pair on top of the sulfur. And this lone pair is going to distort that bond angle, giving us that sort of bent appearance, hence the name bent. So when you're drawing this Lewis structure, you want to bend those bonds down because you want to show that that lone pair on top is distorting that bond angle, making it less than 120. So our molecular geometry here would be bent, but our electron geometry is going to be trigonoplanar because of those 3 domains. So what would happen then if you had 2 bonds but 2 lone pairs instead of 1 lone pair on the central atom? Well, it's going to be pretty similar to when we had the 1 lone pair. The molecular geometry is still called bent, and we still have that less than 120 degree bond angle, but that bond angle is going to be even smaller because now we have 2 sets of lone pairs, distorting that angle even further. So it's pretty similar, except we just have a more exaggerated distortion on that bond angle. And in fact, I wanted to point out that that distortion is so great that it's going to be less than 109.5 degrees now, because now we have a tetrahedral electron geometry, because now we have 4 domains around the central atom. So normally with tetrahedral we would see a 109.5 degree bond angle, but now with this bent structure with 2 lone pairs, we go even further down and we have a bond angle that's less than 109.5 degrees. And a great example of this is going to be water, H2O, where we have our central oxygen with 2 lone pairs on top and 2 bonds going to the hydrogens. And our bond angle here between the 2 hydrogens is going to be less than 109.5. Because now our electron geometry on this is going to be tetrahedral because of the 4 domains, but the molecular geometry is still going to be called bent. So now let's look at if we have 3 bonds coming off the central atom, but 1 lone pair on top. And ultimately, this is going to give us 4 electron domains, which means that our electron geometry is going to be tetrahedral, but the molecular geometry of this structure is going to be called trigonal pyramidal. And our bond angles are going to be less than 109.5 because we have 4 domains. Normally for tetrahedral with 4 domains we would have 109.5, but because of that distortion from the lone pair, it's going to be less than 109.5 degrees on those bonds. A really nice example of this trigonal pyramidal structure is going to be the ammonia molecule, NH3, where we have the nitrogen with the lone pair on top and 3 hydrogens bonded to it. And that's going to give us those bond angles that are less than 109.5 degrees. So remember, your electron geometry for this molecule is going to be tetrahedral because of the 4 domains, and the molecular geometry is going to be trigonal pyramidal because of that distortion from the lone pair, giving us this trigonal pyramidal structure. So what happens if we stick 2 lone pairs on that central atom with 3 bonds? Well, we're going to end up with 5 total domains around the central atom, and that's going to give us an electron geometry that's trigonal bipyramidal. However, the molecular geometry is going to be called T-shape because the structure is going to kind of resemble the letter T. And so we've got those 2 lone pairs and those 3 bonds coming off. And because our electron geometry is trigonal pyramidal, we would expect it to have a 90-degree axial bond angle and a 100-degree equatorial bond angle. But because of those 2 lone pairs, we have a distortion where we have less than 90 degrees and less than 120 degrees for those axial and equatorial bond angles. So a nice example of this T-shaped geometry is going to be the ClF3 molecule, where we have the 3 fluorines bonded to the chlorine in the middle with the 2 lone pairs on top of the chlorine. And that's going to give us those distorted bond angles where our axial bond angles are going to be less than 90 degrees and the equatorial bond angles are going to be less than 120. And overall, remember, our electron geometry for this is going to be trigonal bipyramidal because of the 5 domains, and the molecular geometry is going to be the T-shape that we just talked about. So next up, we've got 4 bonds coming off the central atom with 1 lone pair. And this is going to give us 5 domains again, which means our electron geometry for this structure is going to be trigonal bipyramidal. But the molecular geometry is going to be called seesaw. And that's because the structure is going to take on a shape that kind of looks like a seesaw, with the 2 bonds coming off the bottom and the 2 bonds coming off the sides. And so because of our electron geometry, we would expect it to have a 90 and 120 degree bond angles. But because of that lone pair, we have a distortion, which means that our axial bond angle is less than 90 degrees, and our equatorial bond angles are less than 120 degrees. And like I said, we're going to call this shape, the molecular geometry is called the seesaw. So here's a really nice example of that seesaw molecular geometry with the SF4 molecule. So we'll have our central sulfur with 4 fluorines bonded to it and that lone pair on the top. And here we see our electron geometry is going to be trigonal bipyramidal because we have 5 domains, but the molecular geometry is that seesaw structure. And just note that your axial bond angle is less than 90 degrees and your equatorial is less than 120 degrees because of those 5 domains. So here we have a situation where we still got our 4 bonds, but now we've got 2 lone pairs on that central atom instead of just 1. And because we've added that extra lone pair, we now have 6 electron domains around the central atom, which means our electron geometry is now octahedral. But the molecular geometry, we're going to call that square planar for this structure. And because our electron geometry is octahedral, we would expect 90-degree bond angles all around, but in this case, because of those lone pairs, our distorted bond angle is going to be less than that 90 degrees. So a nice example of this square planar structure is going to be the molecule XeF4, where we have the xenon in the middle, the 4 fluorines bonded around it, and the 2 lone pairs on that central xenon. And this is going to give us that square planar molecular geometry, but our electron geometry is going to be octahedral because we have a total of 6 domains around that xenon, which means our bond angles between these fluorines are going to be less than 90 degrees for each fluorine. And so last but not least, we have our final type of geometry. And that's going to be when we have 5 bonds but 1 lone pair on the central atom. And that's going to give us a total of 6 electron domains, which means our electron geometry is going to be octahedral. So we would expect 90 degrees for octahedral, but again, because of that lone pair distorting the bond angles, it's going to be less than 90 degrees. And the molecular geometry for this structure is called square pyramidal. This one's pretty rare. You don't really see this very often, and I can actually only really think of one example where this is the case for the geometry. And that one example is going to be ClF5, where we have our central chlorine with 5 fluorines going around it, and 1 lone pair, on top of that chlorine. And that's going to give us that square pyramidal molecular geometry, while our electron geometry is going to be octahedral, because we've got those 6 domains around the chlorine. And because of that, our bond angle is going to be distorted as less than 90 degrees for the domains going around this chlorine. So that just about wraps it up. That's the final thing here. Just a few things to keep in mind. Make sure when you're doing these, you draw your valid, correct Lewis structures. Count the number of domains around your central atom. Differentiate between lone pairs and bonds. And then you can start predicting your molecular geometry. And just keep in mind that there's a difference between molecular and electron geometry. Electron geometry is dependent on the number of domains around the atom, the central atom, whereas molecular geometry is going to be the shape and that shape is going to depend on whether there's lone pairs present on the central atom distorting those bond angles, or whether you just have bonds. And in the case where you just have bonds with no lone pairs, the electron geometry is the same as the molecular geometry. So hopefully this clears up anything you might have been confused about when it comes to molecular geometry.